Okay, we're going to talk about something called the complement here. Notice the spelling. It's really not spelled like if you were to pay me a compliment. But the complement A prime is simply the set of all elements in the sample space that are not in set A. And I showed you this picture before where this is set A and A prime would be the elements that are not in the set. Okay, now you can read the development of the complement formulas, but I'm going to just go ahead and give them to you. It turns out that the probability of any event plus the probability of its complement always has to equal 1. Now a very simple example of that is if you know the probability of rain is 0.7, then obviously the probability of not raining would have to be 0.3, so that 0.7 plus 0.3 would equal 1. So basically that's the probability. Now from this probability, you can read the rest of this if you want, but I'm just going to give you the formulas. From the probability, from that formula, we can actually see that the probability of an event is 1 minus the probability of its complement, or we can see that the probability of a complement is 1 minus the probability of the event. Now, this is actually pretty handy because sometimes it's easier to determine the probability that an event did not occur. Then you can just find that probability, subtract it from 1, and that'll give you the probability that the event did occur. And you can pause the video and read this simple example here if you want to. Okay, so let's look at an example. Let's say 2 die are tossed. What is the probability that the die will be different numbers? The die will be different numbers. Well, we know there's 36 possible rows. So let's let A be the event that the dice are different. Well, wouldn't it be easier to figure out A prime, the event that the dice are not different? In other words, they're the same. So I can actually figure that out pretty easy. Remember, there's 6 ways that the dice can be the same. So if I say A prime would be the event that they're not different, they're the same, then the probability of A prime would actually be 6 out of 36, which is 1/6. Now, but I didn't want to know the probability of A prime. I wanted to know the probability of A. Well, once I know the probability of A prime, you just subtract the probability of A prime from 1, and that will give you the probability of A. So 1 minus 1/6 is 5/6. So the probability that the dice are different would be 5 out of 6, you see. And here's another example. 2 dice are rolled. Find the probability that the sum of the numbers rolled is greater than 3. So let's say A is what we're looking for, the event of a sum greater than 3. Lots of ways that could happen. But let's try A prime, the event that we get a sum not greater than 3. Well, let's think about the ways that can happen. How many ways can that happen? Well, 1, 1 is a sum of 2. That's not greater than 3. 1, 2 is a 3. That's not greater than 3. 2, 1 is a 3. That's not greater than 3. So there's only 3 ways that we can get A prime to occur out of 36. So the probability that A prime occurs is 3 out of 36, which reduces to 1/12. But again, I didn't want the probability of not A. I want the probability of A. So to get the probability of A, I just take 1 minus the probability of not A, which is 1 minus a 12th, or 11/12. Okay. Now, we could have solved those other examples without using the complement, but let's take a one that just about forces you to use the complement. Let's say 8 cards are drawn from a standard deck. What is the probability that we get at least 1 face card? Okay, well, we're looking for the event that we get at least 1 face card. Well, at least 1 face card would mean I'd have to know how many hands have exactly 1 face card, how many hands have exactly 2 face cards, how many hands have exactly 3, how many hands have exactly 4, 5, 6, 7, or even 8. Well, that's a lot of probabilities that I'd have to calculate, and then I'd have to add them together. But actually, if you think about the complement, E prime is the event of not getting a face card. So not getting a face card, well, that would be 0 face cards. Well, we can easily find the probability of getting 0 face cards. So the probability of getting no face cards would be out of the 12 face cards, choose none, and then out of the 40 other cards, choose all 8, and then of course divide that by the number of ways you can choose 8 cards from a deck, which is 52, choose 8, and you get 0.1022. And then you can subtract 0.1022 from 1 to get the probability that we were looking for, 0.8978. Okay, let's talk about the birthday problem, but I don't want to spend a lot of time on it. How many people would you randomly select in order to expect there to be a 97% chance of 2 or more having the same birthday? Now, you might find this surprising. Basically, the birthday problem says we want to find the formula for finding the probability of 2 or more people having the same birthday. Well, actually, you can actually show that this formula gives you the probability of no one having the same birthday. So if E is the probability, if E is the event of 2 or more having the same birthday, then E prime would be the event that nobody has the same birthday. Now this is based on N people, so the N just represents N people selected. Well, if you know that this is the probability of not E, then you can find the probability of E that 2 or more have the same birthday by subtracting that from 1. Okay? Now, if you do some calculations, for 30 students, you're going to get about a 70% chance. And actually, when you get up to around 47, 48 students, I believe is where you get 0.97. So believe it or not, you don't have to have as many students as you might think. Now, you can skip this if you want, but let me just go ahead and show you. We know we have N people. So for N people, to get the sample space, I've got to consider how many birthday lists are possible, how many birthday combinations are there. Well, everybody in the room could be born on any of the 365 days. So person A could be born 365 days, person B could have 365 days for their birthday, person C, and so forth. And you multiply this out N times, and you get 365 to the N. So that's how many possible birthday combinations there are. And that was the easy part. Now that's the sample space. Now let's talk about, we got the denominator, let's talk about the numerator. Let's say E is the event of 2 or more having the same birthday. Well, I said that's too hard to calculate. So let's let E prime be the event of no matching birthdays. Well, it turns out that if you start to count those numbers, we could say, well, person A can be born 365 days, but no matching birthdays means no repetition. So the next person has to be born 364 days, the next one 363 days, and so forth. And it actually goes down to the number 366 minus N, where N is the number of people in the room. So I'm not going to explain why, but that's basically where it goes down to. Alright, so now let's return to the probability of not E. So we know for the probability of not E, the bottom has to be the number in the sample space, 365 to the N, and the top has to be this guy, 365 to 364, and so on, to 366 minus N. Okay, well, there's a little trick that you can do to make this. We can actually multiply the top. We can multiply the top by 366 minus N, or 365 minus N minus 1 factorial. Now, don't get lost in this, but let me just tell you this. If you take this and you multiply it by this, well, what it's going to do is it's going to make this go 365, 364, 363, and then it'll just continue going all the way down to 1. Okay? And so if you have that on the top and bottom, that's what you're going to have. And by the way, this is supposed to say, not supposed to be the probability E, but anyway, let me just show you the formula. So basically the formula is calculated right here. If there's 5 people in the room, then this would go down to say 365 to 361, and then we would multiply by 360 factorial over 360 factorial, and what that would do is that would cause this entire top to be 365 factorial, and then the bottom would be 365 to the n times 360 factorial, and then we actually would get this expression. And by the way, the n should be a 5. So that should be a 5. So everywhere you see it in there, that should be a 5 if n is 5. So anyway, this is the general formula for the probability of not E. So if you want the probability E, you subtract that formula from 1. Now, so if you took some numbers, some values of n, and plugged it in here, if you can find a calculator that will calculate it, notice what you'll get. And again, don't worry too much if you don't understand this, because I don't really have time to go over it. But if you do 23 people, you're going to get over a 50% chance of having a matching birthday. If you do 50 people, you got a 97% chance. If you do 100 people, you've got a 99.99997% chance. And in order to get a 100% chance, you'd have to go 366 days so that you would be guaranteed that at least 2 people had matching birthdays. So it's an interesting problem, but don't lose too much sleep over it. Okay, take this one as a practice problem. And this one is actually a little bit like the problem I did earlier, where you're selecting 8 cards from a deck, and you want to know the probability that you have at least one face card. Well, here you want to know the probability that you get at least one defective item. So it's basically the same thing, except for face cards, it's defective items. So pause it, work this, read through it if you have to, and see if you can get the answer that I got, and see if you can follow it. And now I want to move on to one last thing. Now here, converting probability to odds and odds to probability. The probability of an equally likely event E is this ratio, the number of ways the event can occur over the total possible outcomes. But the odds in favor of an event E occurring is the number of ways the event can occur to the number of ways the event cannot occur. So here's what I want you to understand. Let's say you know the probability of an event occurring is 7 out of 11. Well, that means there's 7 ways it can occur out of 11. So how many ways can it not occur? Well, 7 from 11 is 4, so it would be 4. So then the odds in favor of the event occurring would be 7 to 4. And you can write it in multiple different ways, but the odds in favor would be 7 to 4. Okay, let's look at another one. If the probability of an event occurring is 8 out of 31, then to convert that to odds, you say, well, how many ways can it not occur? Well, 8 from 31 is 23, so there's 23 ways it cannot occur. So the odds in favor of the event occurring is 8 to 23, and the odds against would be 23 to 8. You just turn it around. Okay, now if you want to convert from odds to probability, you do it the other way. So the 7 to 5 means there's 7 ways for the event to occur to every 5 ways it can't occur. Well, if 7 ways for it to occur and 5 ways not to occur, well, that's 12 possibilities. So if the odds are 7 to 5, then the probability would be 7 out of 12. Now, there's formulas that you can look up, but you don't have to really do it if you understand what odds are. Again, the probability is 7/9. Then I know there's 7 ways it can occur to the 2 ways it cannot occur, so the odds are 7 to 2. If the odds are given 8 to 5, then the probability would be 8 over 8 plus 5, which is 8 out of 13. So that's how you convert probability to odds and odds to probability. They're related, but odds and probability are not exactly the same thing. Okay, so read these 2 problems, freeze the video if you need to, and freeze them and work those on converting probability to odds and odds to probability, and that should shore up your knowledge on odds and probability. Okay, I'm going to leave you to read this application problem. Pause the video, read it, work the problems the way I did. It asks for probabilities and it asks for odds. But notice I used a Venn diagram to solve it, and I think from the picture you should be able to figure out how to answer the questions. And that's pretty much it on this section.